Okey-doke. Hopefully the multimedia system is on. All right, looks good, thank you. So is it unlocked now? I guess I can unlock it myself. Can you turn it? See maybe? Good. Okay, now you can come in. We were going to lock you in here. Just leave you. Do you mind closing that outside door? Thanks. So the last homework set, you can pick it up after class. Obviously there's no other homeworks. Hopefully you had a chance to study the practice exam that I gave you. I'm going to go over it today. And the final is next week here. And for the final, just to give you a little bit of information, the final is, of course, a 3-hour exam, which covers everything in the class, including the stuff that we've done after the midterm and the stuff that we did before the midterm. For the exam, if you remember, for the first exam, for the midterm, you were allowed 1 sheet of paper this size. For the final, you're allowed 2 sheets of paper, same size. You can write whatever you want on it. Again, same deal, no books, no notes, no calculators. Okay? Any questions? Don't ask me how hard or easy it's going to be, because I'll just say hard. Okay? All right. So the agenda today, if you remember from last time, was I'm going to do a review and also go over the practice exam. But before I do that, I realized as I was going through the lectures last time was that I never quite told you exactly why this repeated applications of the filter was called diffusion. So I'm just going to spend maybe 5 minutes telling you why this thing is called diffusion before I go on. By the way, did everybody get my email about the course notes? So all of the notes, stuff that I've written here is now scanned in PDF form, also with the recordings. They're all in the same directory. Now you can watch them at the same time if you need to. If you have any problems accessing the material, certainly let me know. Okay, so let me spend a couple of minutes just talking about the relationship of these filters to diffusion. Okay, so relationship to the diffusion equation. Okay, so first of all, let me remind you the filter that we were talking about is this z hat k equals w z hat k minus 1. Okay? And the idea here, in order to turn this into something that looks like a diffusion equation, what I'm going to do is a couple of simple algebraic manipulations. So I'm going to add or subtract z hat k minus 1 from both sides of this. Z hat k minus 1. Z hat k minus 1. Okay? So just subtracted this from both sides. Then this right-hand side is w minus the identity times z hat k minus 1. Okay? Now, it turns out that this here, w minus I, if you remember, we thought about w as a blurring matrix, right? Something that essentially acted as a low-pass filter with all positive coefficients, averaging, and so on. So if w is a low-pass filter, then w minus I is a kind of high-pass filter. Okay. So this right-hand side is basically talking about applying a high-pass filter to the last estimate, zk minus 1. As a matter of fact, it turns out that this can be written as d to the minus 1/2 L d to the minus 1/2. I'm not going to show you the derivation for why this is the case, z hat k minus 1, where in fact this L is the Laplacian operator. Okay? And d to the minus 1/2, this d is that diagonal matrix that we used, which along the diagonal had the normalizing coefficients, right? So when we wrote w equals d inverse k, that d is the same d here. Okay? So this literally is a Laplacian operator, so it's a matrix manifestation of the Laplacian operator. So now, in order to turn this really into what I call the diffusion equation, you just make some very simple changes of variables. You define zk bar as d to the 1/2 zk hat. Okay, so it's just simply a scaling of these coefficients. And with that, then you can rewrite all of this. The left-hand side and the right-hand side can be written as z bar k minus z bar k minus 1 equals the Laplacian operator times z bar k minus 1. Okay? Now, these are measured or they're stated in terms of a discrete index, right? K, k minus 1, k minus 1, and so on. But this left-hand side can be thought of as a discretization of a derivative. So if you think of z bar as evolving not as a function of an index, but as a function of time, then this is approximately something like z bar of t minus z bar of t minus delta t divided by delta t. Okay? Which really is just a derivative. Okay, so the limit of this as delta t goes to 0 is in fact the derivative. So this is d z bar t dt. Okay? And this is the Laplacian operator applied to z bar k minus 1. So this right-hand side is basically, in the continuous world, it's the Laplacian operator applied to z bar t. Okay, so this here is the continuous equivalent of this discrete equation. And now if you look at this, this is exactly the diffusion equation. It's a heat diffusion equation. Okay, defined in terms of z bar. And what is the solution to this diffusion equation? Right? If you go back and look at your physics or differential equations class, or partial differential equations class, the solution to this equation is, or the fundamental solution to this equation, is z bar of t equals y of t, where y of t is the initial conditions, convolved with a Gaussian. Okay? So if you look at what this is doing, as t evolves, then the input, which is your noisy data, keeps getting involved, it keeps getting convolved by Gaussians again and again and again. And this is really nothing but this equation. Okay? So remember, this was equivalent to z bar or z hat k equals w to the k y. Right? So you can see how this is related to that, because this is basically, W is a matrix that's built from this Gaussian kernel, right? And so the two are intuitively very much the same. Okay, so this is the reason why this is called the diffusion equation. And the other one, which was the residual iteration, that also has a very similar interpretation. So the residual iteration, remember, is z bar, z hat k equals z hat k minus 1 plus w times y minus z hat k minus 1. Okay, so we do something very similar here. Again, we just write this out. I can subtract from both sides a z hat k minus 1. And what I get is z hat k minus z hat k minus 1 is equal to z0, I'll tell you what z0 is in a second, minus zk minus 1 plus d to the minus 1/2 Laplacian d to the 1/2 z hat k minus 1. This z0 here is simply w times y. Okay, so it's just applying the filter once to the data. And so if you look at this, if you just completely ignore these two terms, then what you have is exactly what you had before, which was the diffusion equation, right? So what you have is the diffusion equation plus a forcing term. This is called the reaction diffusion equation. So if you just rearrange everything, what you have is, again, the same set of calculations. What you end up with is z bar k minus z bar k minus 1, same definition as before, is equal to the Laplacian operator applied to z bar k minus 1, that's this term here, plus z0 bar minus z bar k minus 1. Okay, so this part here is just a Laplacian, and this is a term which sometimes is called the bias term, sometimes it's called the forcing term. And what it's doing, and this z0 is what you might call a pre-filtered version of the data. You filter it once and then you stop. This, what it does is it biases the solution towards this pre-filtered version of the data. Okay? It forces the solution not to get too far away from that initially blurred version of the data. So another way to write it is, again, in the continuous world, dz bar of t dt equals the Laplacian z bar of t plus a bias term. And this here is called reaction diffusion equation. Okay? All right, any questions about this?
Is this this is a matrix Laplacian operator? So
This is a matrix Laplacian operator.
So then it's just a diagonal matrix with dx sub 1 squared and so forth into diagonal elements?
Yeah, so this is actually, this Laplacian operator is what in general we call an anisotropic Laplacian operator. It's actually a nonlinear Laplacian operator because in the general case, the Laplacian operator, which depends on W, depends on the data as well. Okay, so generally the Laplacian operator is just a derivative operator, right? It's just an operator that's perfectly defined regardless of what the data is. But what we do is we define a Laplacian operator from the kernel. And the kernel can depend on the data itself.
So how does that look like?
What do you mean, how does it look like?
I mean, I have no problem with...
Oh, you mean algebraically, how does it look like?
Yes. Sure.
Okay, so yeah, what algebraically, what the Laplacian operator looks like is something like this. It's something like, let's say you have the derivative operator in the x direction and the derivative operator in the y direction, right? So let's call those delta x and delta y. So it's something like delta x, ax, delta x, delta x transpose ax delta x plus delta y, ay, delta y, like that. Okay, so forget about ax and ay for a second. So this is exactly the Laplacian, right? You're applying the two x derivatives and two y derivatives. Okay? Now the ax and the ay are a bunch of coefficients. So ax and ay can be a diagonal matrix, each of them, which give you different weights depending on the points that you're looking at. Okay? So the kernel k appears inside these, the ax and ay. If you want to give different weight to different points away from the center, you put those in a diagonal matrix in ax and ay. Okay, but otherwise, this would be the standard Laplacian operator. Okay? And when you put these in, and ax and ay depend on the data, then it becomes a non-linear Laplacian operator, which is the general form that we use it. Does that help?
Yeah.
Okay. All right, so this is all I want to say about this. Hopefully it's a little bit more clear now what we mean by diffusion and reaction diffusion. Okay, so now from this point forward, I'm just going to do the review. So I'm going to do the review in a kind of backwards fashion, starting with the estimation. And then at the end, the last half an hour or so, we will we'll just go over a bunch of problems. Okay, so the concept of estimation is that you're trying to extract a parameter where a bunch of data give you some information about that parameter. So you're going to have a bunch of data, let's say x1 through xn, and the estimate is going to be theta hat equals some function, let's say g of this data, x1 through xn. Okay? Every estimator is going to be measured by its bias and variance characteristics. And the choice of every estimator is essentially a balance or a trade-off between bias and variance. So whether you do maximum likelihood, maximum a posteriori, Bayes minimum mean squared error, non-parametric estimation, these are all just different ways of trading off bias against variance. And so to remind you, the bias, let's call it b of theta. This is the expected value of theta hat minus theta. And the variance is the expected value of theta hat minus e, theta hat squared. This is in the scalar case. And in the vector case, when you define a covariance, theta hat is expected value, theta hat minus e, theta hat minus e, theta hat transpose. Okay? And so the mean squared error, then in the scalar case, is the variance of theta hat plus the square of the bias, or the definition of the mean squared error, the expected value of theta hat minus theta squared. It's very important not to confuse the definition of mean squared error with the definition of the variance. In the variance here, you're subtracting from the expected value of theta hat. In the mean squared error, you're subtracting from the actual value of the underlying parameter. So this doesn't require you to know the truth. This requires you to know the truth. Okay? And for the vector case, the mean squared error matrix, as we might call it, is the covariance of theta hat plus the outer product of the bias vectors, or the bias vector. And for the vector case, we can also define a scalar mean squared error, which is the trace of the vector mean squared error matrix. Okay, so if we do that, this is the trace of the covariance of theta hat plus the trace of this matrix. Remember, this is a matrix. It's an outer product, so it's an n by n or p by p matrix. And the trace here can in fact be written as the norm of b of theta squared. Okay? So the trace of this matrix is in fact b transpose b, which is nothing but the norm of b squared. Okay, so with this in place, then we went on and defined various different criteria for doing estimation. So there were two types of problems that we considered, one in which the parameter of interest was random, and one in which the parameter, and the other, the parameter of interest was deterministic. The deterministic case is, of course, simpler. And so if you wanted to define, let's say, the minimum mean squared error estimate in the deterministic case, you're going to look at the norm of theta hat minus theta, the expected value here. And this expected value is going to be computed over the data, right? On the other hand, in the random case, the mean squared error is going to be an expected value of the norm of theta hat minus theta squared. Sorry, the squared here as well. So that here, it's not just over the data, it's also over the parameter. Okay? So you have to be careful about the definition of the mean squared error in the random versus deterministic case. Theta hat depends on the data, right? So the only thing that's random in this case is the data. In this case here, you have two random things. One is the data which defines theta hat, and the other one is the actual value of the parameter. Okay? So the question then was, is it possible to come up with estimators that minimize mean squared error? What we saw was that in the deterministic scenario, it was not always possible to come up with a minimum mean squared error estimator. Or if you did, they were not realizable in the sense that the estimator would depend on the value of the unknown parameter, which means that it's not practical. Okay. In the random case, we saw that there was a very particular way of doing mean squared error minimization, which was the Bayes mean squared error, which is kind of this quantity here. And in that case, we could see that if you had two parameters that were dependent on each other, then the conditional mean of one parameter gave you the optimal mean squared error estimate of the other parameter. Okay. And the advantage here is that because So the difficulty with the deterministic case is that minimizing the mean squared error depends on knowing the truth, right? What this says is that it's okay if you don't know the truth, because you know the distribution over it and you're taking an expectation with respect to it, then you can come up with mean squared error minimization. Okay? It's a little bit of a magical coincidence that this happens. Okay? So Bayesian minimum mean squared error works. Deterministic minimum mean squared error is often not realizable. Okay, so going back to the deterministic case, we realized that minimum mean squared error was not always possible to do, and so we made some compromises, and one of them was to come up with minimum variance unbiased estimators, and that was the case where you come up with estimators, all of which satisfy this constraint. The bias is equal to 0, and then you minimize this, you satisfy this constraint while trying to minimize the variance of the estimate. And again, we saw that this even was difficult to find because it may in fact be impossible to even find unbiased estimators for certain types of problems. However, you saw that for the linear problems, we could come up with unbiased minimum variance estimators for the case where you had the signal model x equals h theta plus noise. For that, we could come up with these types of estimators. And in fact, even if the Gaussian was not your noise assumption, if the noise wasn't Gaussian, you could still come up with minimum variance unbiased estimators by basically using a linear estimation structure. Okay, so we'll talk a little bit more detail about that a little while later. So another approach that we took, which was much more mechanical, much easier to carry out, was the maximum likelihood. And the idea behind maximum likelihood was that you would take PDF of the data given the unknown parameter, and you would maximize this over theta. And this would give you the ML estimate. The nice thing about this structure was that it was very easy to carry out, because if you know this PDF, if you know this conditional PDF, then maximizing it is just simply a matter of taking the derivative, setting the derivative equal to 0, getting an answer, and then making sure that the second derivative is negative so that you have a maximum. Okay? And also, typically, we don't maximize p of x directly by itself. Instead, we take the log of it and maximize that. And that's a perfectly okay thing to do, because log is a monotonic function, so it's not going to change the location of the maximum of this function. Okay? So the equation that we typically ended up using was PDF of x given theta, log of the derivative of this with respect to theta equal to 0, and the solution to this gives us maximum likelihood. Okay? And if you remember, this thing here is called the score function. Okay, why was this a good idea? I just said one of the reasons it's very mechanical, it's very straightforward generally to compute these things. And even if it isn't, you can compute numerically an approximation to the maximum likelihood estimator by simply treating this as a nonlinear equation in theta and solving. But perhaps the most useful or most important reason for the maximum likelihood estimator to be useful is the asymptotic properties that it has. Namely, asymptotically, in fact, thought of as a random variable, asymptotically, it has a Gaussian distribution with mean theta and covariance, which is I inverse of theta, where this I is the Fisher information matrix. Okay? So basically, the bottom line here is that the maximum likelihood estimator is asymptotically the right thing to do. Okay? It gives you an unbiased result, and asymptotically, in fact, it achieves the Cramer-Rao lower bound. Okay, now asymptotically is not always a practical thing to have. This asymptotic result requires you to have a huge amount of data or very little noise, one or the other. Okay, and that's not always going to be the case generally. Okay, so this, an extension of this was the idea of maximum a posteriori estimation. Or map. Now in this case, you had not only the conditional density of the data given the unknown parameter, you also knew something about the parameter, namely its probability density function. And so with access to that, all you do is you multiply these two together, and this multiplication, what it does is it simply biases the maximum of this quantity in the direction of the most likely values of theta, which you know ahead of time. So this piece of information is completely given to you before you ever collect data, right? And this piece of information comes directly from the data. So the maximum a posteriori can be thought of as a way of balancing prior information against information that you get from the data. Okay? So again, the idea is that you maximize this over theta, and that gives you theta hat maximum a posteriori. And the maximum a posteriori equation, log of p of x given theta, theta plus log of p of theta, p theta equal to 0. So the solution to this is in fact the maximum a posteriori. Now, when do the two situations coincide? If the P of theta is not informative, in other words, if P of theta doesn't give you any reason to believe that any value of theta is any more likely than any other value of theta, then this term is simply going to disappear. Okay? So one example of that was that if the parameter theta is defined over a finite interval, then over that finite interval you can give P of theta a constant density, like a uniform density, in which case the log of this whole thing is just going to disappear. And then you have back your maximum likelihood estimate. Okay? All right, again, maximum a posteriori is also very mechanical. This, you can think of this as a nonlinear equation. It either gets solved in closed form or it gets solved in numerical fashion, either way. Yeah.
In Bayesian estimation, do we minimize the Bayesian risk?
Yeah, essentially what you end up doing is you're minimizing a kind of Bayesian risk. And the Bayesian risk that you minimize here is, for the estimators that we talked about, the Bayes minimum mean squared error, what you're minimizing is the joint density of the data and the unknown parameter. Okay?
Yeah. So
Essentially that's what you use.
So in Bayesian estimation, generally we will finally reach to such an equation with some coefficients of each, the risk for each case.
I'm not sure what you mean by risk for each case.
Can you explain the Bayes estimation?
Yeah, I'm getting to that next. Okay? So the Bayesian framework, well, this is also Bayesian. Okay? So let's just be clear. There's two different kinds of Bayesian we can do, right? One of them is where you simply use a prior density on theta. And the second is when you do Bayesian minimum mean squared error. Okay? The Bayesian minimum mean squared error, what the idea behind this was that you have a probability density for x and theta jointly. Okay? And what you're going to do is you're going to come up with an estimate that looks like this. Theta hat is the expected value of theta given y. Okay? Now, how is this different than this framework? The idea here was, remember, this formulation could also be written as maximizing P of theta given x, right? So the difference between these two is that in this case, what you're looking at is you're looking at the maximum of the posterior distribution. This is the posterior distribution of theta given the data. Whereas here, you're looking at the mean of the posterior distribution. So what we had was a situation where, let's say, you might have a posterior that looks like this. It's PDF theta given x. Okay? And in this case, your maximum a posteriori estimate, which is a Bayesian estimator, is in fact at the peak here. So this would be theta hat map. Whereas in this case, you actually look at the expected value, which because this is asymmetric would probably occur here. Okay? So this would be theta hat Bayes mean squared error estimate. Okay, so the question, I guess, going back to what you said initially is, what are you maximizing? Well, in this case, what you're minimizing is what I wrote earlier, which is this. Let's see, where is it? This is what you're minimizing. Okay. Whereas in the map scenario, this is what you're maximizing. Okay, so the costs are quite different. They're definitely not the same. Now, you might ask, is there another way to formulate the Bayes mean squared error so that you have other penalties attached to it? So let's say you want to minimize this plus some other penalty attached to the estimates that you. Certainly there is. Yeah, you can do that. That has a slightly different interpretation. Then I can't easily write them in terms of the maxima of the posterior distribution. Okay. All of this depends on knowing very specifically what the distributions are. So from a computational point of view, all I have to give you here is I have to give you the prior density for theta. Right? That's all I need to give you. Whereas in this other case, I have to give you the joint density. Now, of course, you can compute the joint density from here as well. But the difference here is that the joint density is going to involve actually a multiplication, and then you have to normalize, which is going to involve some integration, and so on. So it's not a trivial step to go from this estimator to this estimator. Here, I'm giving you the joint density, end of story. Okay, so you can then go and compute your Bayes mean squared error estimate. Okay. All right, so when do these two, map estimate and the Bayes mean squared error estimate, when do they coincide? Well, obviously, in a situation like this, they're going to coincide when this posterior distribution is unimodal and symmetric. Right? So if the maximum and the expected value are the same, when does that happen? It happens when the posterior is symmetric. Okay. So one case in which this happens is when theta and y, or theta and x, I should say, this is x, not y, sorry. When theta and x are both jointly Gaussian. Okay. So in that case, the Bayes minimum mean squared error is the same thing as the maximum a posteriori estimate, because everything ends up being symmetric around the mean. Okay. All right, so then we kind of moved on to more flexible ways of doing estimation when we don't necessarily have the distribution for the data. And probably the most flexible of all of these was least squares. Okay, now this least squares that I'm talking about here is parametric least squares. In other words, you're going to assume that your signal has a global parametric model. Okay, so all the data depend on the parameter in a very specific way. And then you use that knowledge to compute an estimate of the following sort. So let's say your data might look like, let's say x is equal to s of theta plus noise. And if you assume that this noise is zero mean. Yeah?
Suppose we have the joint probability distribution, and then how should we decide to choose whether to use Bayesian estimation or MAP estimation?
Well, if you
Just
have
we
the
look-
joint density, sorry, go ahead.
Just we look to the complexity of the problem. And if-
Generally, yeah, the complexity of the problem is mostly what dictates which one you're going to use. But also, in the maximum a posteriori framework, what you are doing is you're giving a very explicit interpretation of your prior information. Okay? So you're saying, I know something very specific about how this parameter behaves, regardless of what the data is. Whereas here, you're giving information about theta only in the context of how it interacts with the data. Right? So philosophically, they're sort of different ways of doing things. Also, the maximum a posteriori has other interpretations. If you just take this quantity and take the log of this quantity, then you have the log of p of x given theta plus the log of p of theta, right? Now, the log of p of theta, you can just think of it as a penalty term. And then you can put whatever you want there, as long as it's positive and well-behaved. And then you have an interpretation for any kind of regularization, any kind of penalty that you put on the parameters. You can interpret that as a prior information on theta. You can't do that here very easily. In other words, if you wrote your minimum mean squared error and then you penalized theta independently, I can't interpret that very easily anymore. Okay? So it's really a question of, certainly complexity plays a big role in it, but it's also a question of interpretation. Okay? Typically, if you come up with prior information directly, then this is what you want to use. Okay? All right, so with least squares this way, what we're saying is this kind of model is what I'm calling a global model, because I'm saying the parameter which the signal depends on affects all the data points, all at once. This is different from the local framework that we use later on with the non-parametric methods, where we said, okay, we're going to estimate a parameter, but that parameter is only for a local approximation to the signal around some window. And then when we move, we use a different parameter. Okay. So with this framework, then what we did was we said, okay, the theta hat, least squares, this is the minimizer over theta of the norm of x minus s of theta squared. Okay? Now, if it so happens that this noise here is zero mean Gaussian white noise, then the minimization problem, when you write down the maximum likelihood, is exactly the same thing. Okay, so they coincide. However, I didn't need to make that assumption in order to write this down. I just picked the criterion to minimize, which was this, which is why this is called least squares. And all I need for this to be a reasonable criterion to minimize is expected value of w is equal to 0. Okay? All right, now this here is a nonlinear least squares, which means that I cannot solve it in a closed form. So if I call this here, j of theta, then my solution to this minimization problem would be to differentiate dj d theta, set it equal to 0, and then think of this as an equation, g of theta equals 0, and solve this equation in some fashion. Okay? Now, more specifically, if the signal s of theta here has if the signal has a linear model, let's say h theta plus w, okay, then the least squares problem is minimizing over theta the norm of x minus h theta squared. And if you take the derivative of this, now here theta appears in linear form inside the square. So this is a quadratic cost function in theta. You minimize it, set it equal to 0. What you get is theta hat equals h transpose h inverse h transpose x. Okay, so now you have a closed form solution, whereas here you did not have a closed form solution. Okay, the nice thing about least squares is that you don't need to make any statistical assumptions aside from the fact that the data is, the noise is zero mean. It is equivalent to maximum likelihood in the Gaussian case, when the noise is Gaussian white. And even if it's not white, then it's just weighted least squares. And again, that's still equivalent to maximum likelihood. And then finally, we talked about doing penalizing this instead of just minimizing that norm, x minus h theta norm squared. We talked about minimizing this plus some coefficient lambda times some function r of theta, which is a penalty on theta. And we talked about how this has exactly the interpretation of maximum a posteriori, where this is the data term. If the noise is Gaussian, it's exactly the same as maximum likelihood. And this basically has the interpretation of a prior distribution on theta, which has the form e to the minus r of theta with some normalization coefficient in front of it. So this is basically a prior distribution. Okay. All right, so maximum likelihood is like least squares. Maximum a posteriori is like regularized least squares, which is what this is. Okay? And all of these coincide if the noise is Gaussian and the prior is also Gaussian. Okay? Okay, so let's just, for the sake of completeness, also write down the, so this is the standard least square solution, the weighted least square solution. Weighted least squares is h transpose wh inverse h transpose wx, where these are the weights. So what you're minimizing is not just this anymore. What you're minimizing is x minus h theta transpose w x minus h theta. This is not the same w as I've been using before. Please don't be confused by that. You minimize this over x, so this w ends up in here. Another role that this w can play is that if this data, if the noise has a covariance c, then the cost that you're going to minimize would have a C inverse in here. So this W can play exactly the role of the inverse covariance matrix, and you get the same answer. Okay, and for the Gaussian case, let's see. For the Gaussian case, if you also assume, so if data is a Gaussian, so W is normal, zero mean, and covariance C, let's say, and theta is also Gaussian with zero mean and covariance, let's say, Q, then theta hat, this is the maximum a posteriori, is equal to H transpose C inverse H plus Q inverse H transpose C inverse X. Okay. So it's important to remember the geometric interpretation of least squares as well. So I want to remind you that the geometric interpretation was that the signal you're going to reconstruct, in the linear least squares case anyway, the signal that you're going to reconstruct is going to be a signal that lives in a space that is spanned by the columns of H. Now, even more generally, if you look at this argmin norm of x minus s of theta squared, then this signal s lives in some space, right? The space may not be a plane like I drew for you. It may be a much more complicated manifold. Manifold is just another complicated looking surface, right? So this s of theta, if this was just simply h times theta, then this signal would live in a subspace which was spanned by the columns of s. Columns of h. If s of theta is not a linear function of theta, then maybe there's some other complicated surface along which this signal lives, right? So s of theta is going to live here. Okay. So the bottom line was the data is not going to live in this space because it's been corrupted by noise. And what least squares does is it projects it down perpendicularly, and it gets an estimate of the signal, which minimizes this distance, which is the error. And that's exactly what this error is. When it gets minimized, that's exactly this orthogonal distance. Okay. And it has the same interpretation if S lives in this complicated space. It's still a projection, except that the projection is not onto a plane, but it's onto a more complicated surface. Okay, constrained least squares. I'm not going to go over the details, but the idea being that what you're going to minimize is you're going to minimize x minus, this is for the linear case, this subject to some constraint a theta equals b. And the idea here was that a theta equals b has to be a small set of constraints. In other words, this a has to be kind of a matrix that's broad and thin. Otherwise, if A is square and full rank, then this exactly determines A, and there's no problem to solve. Okay, with this in place, the idea was that the constrained least squares solution is in fact the least square solution plus some gain times the difference between the two sides of this when that unconstrained least squares solution is plugged in. Okay, so this kind of corrects for deviations from that constraint. Okay, what we talked about so far was least squares with more equations than unknowns. And when you have fewer equations than unknowns, then this h theta plus w, your h might have a form like this, which means there are fewer rows here than columns. The columns are the number of parameters, and the rows are the number of equations. So when this is the case, then you have to have another constraint to make sure you get a unique solution. And there we used the minimum norm constraint. We said minimize the length of the solution that you get, subject to x equals h theta. And of course, in this case, you can exactly satisfy this equation. So when you solve, what you're going to get is h transpose inverse times x. Okay? Not to confuse this with the standard least squares solution. Very important to keep them separate. So this is the standard least squares for an overdetermined system where h has a shape like this. Okay, and this is the underdetermined least squares where h has a shape like that. Okay. A few notes about, I'm just going to kind of orally mention these. The Kramer-Rao bound is a way of lower bounding the performance of any estimator. If the estimator is unbiased, then we use the standard form of the Kramer-Rao lower bound, which says that the variance of the estimate is lower bounded by 1 over the Fisher information for the problem. And the Fisher information for the problem is the expected value of the square of the score function. So you take the derivative of the log. So this one way to look at it is you take the derivative of the log of p of x given theta. You square it, and you take the expected value of this. That's one way to compute the Fisher information. This is in the scalar case. Another way to compute it is it's minus the expected value of the second derivative of the log likelihood function. Okay, these are exactly equivalent, this or that. Okay, so this is a bound for the unbiased case. For the biased case, there's an additional term here that takes into account the value of the bias. Okay, one of the things that we had a little trouble with last time in the midterm is the difference between having a minimum variance unbiased estimator and having an efficient estimator. A minimum variance unbiased estimator is an estimator that has the smallest variance in the class of all estimators that have zero bias. That's all it means. Okay? In other words, a minimum variance unbiased estimator does not have to achieve this bound. It just has to be the smallest variance estimator in this class of unbiased estimators. Okay. On the other hand, if you have an efficient estimator, that means that it also achieves this bound. So it is the minimum variance unbiased estimator, and it has covariance that is exactly equal to this. So when this equality is reached, when the variance of theta hat is in fact equal to 1 over I of theta, and you have an unbiased estimate, then you have an efficient estimate. Okay. And efficiency is something that can be achieved either with a finite amount of data or asymptotically. In other words, you may have an estimator that does not achieve this lower bound for a finite n number of samples, but as the number of samples goes to infinity, it gets very large, you might in fact achieve this bound. In which case you call the estimator asymptotically efficient. Now there might be, in your mind, you might be thinking, well, if the number of data points goes to infinity, doesn't it mean that I'm always going to get a perfect answer? And the answer is no, you won't. Okay? In other words, the lower bound doesn't necessarily go to 0, and neither does the variance of your estimator. But as they get smaller, they might get closer to each other. Okay? And that's all asymptotic optimality means. Yeah?
Is a minimum bias estimator and
Minimum
efficient-
variance?
Yeah, bias. Minimum bias.
Zero bias. We've never done anything called minimum
If you
bias.
consider the bias, then the minimum estimator would be efficient estimator.
I'm sorry, say that again? I didn't catch the question.
If we do not set the bias to be equal to 0,
Mhm.
then the minimum estimator would be an efficient estimator.
Right, so in that case, efficiency is defined not by this expression, however, it is defined by the expression that involves the bias as well. Right, so if you want to say an efficient, if you want to call a biased estimator efficient, then it has to achieve not this bound, but the corresponding bound that has the bias term in it as well. Okay? That's just the definition. Okay, the other main subject, which was really not that complicated, that we did after the midterm, was composite hypothesis testing. And the idea here was that if you had two different distributions for each hypothesis where there were some unknown parameters, then so the composite hypothesis test was, let's say you have P of X given H1, and there's some unknown parameter theta 1 in this case, and P of X given H0 with some unknown parameter theta 0. Okay? Unknown parameter in both cases, yes?
No question about the last slide.
Uh-huh.
So an efficient estimator always reaches the CROB
For every value of the parameter.
for every value of the parameter,
Right.
with or without bias. Like, if there is bias, the bias gets accounted for in the
In the CRLB, that's correct. That's right.
So then, an efficient estimator can have bias.
Yeah, I mean, if you properly define efficiency, efficiency is defined by it reaches the Cramer-Au bound. So if you define the Cramer-Au bound for the bias case, then yes. Does that make sense?
Yeah.
Okay. All right, so if you have a situation like this where you have two unknown parameters, then the standard likelihood ratio test is not going to give you optimality. Likelihood ratio test was fix the false alarm rate and you get a maximum probability of detection. In this case, if the parameters are unknown, you take whatever data you're given, and you construct the maximum likelihood expressions for theta 1 and theta 0. You simply divide this, and this is then what we call the GLRT, and then this gets compared to a threshold gamma. And these theta 1 hat and theta 0 hat are the maximum likelihood estimators. That is the definition of the GLRT. If you stick in other estimators in here, you can't call it GLRT anymore. You have to call it something else. Okay? All right. In general, this does not have any optimality conditions. It does not have any optimality properties. However, if theta 1 and theta 0 are very close to each other, and we know that theta 1 is bigger than theta 0, so what we have is a one-sided test, then you have a local optimality. In other words, for values of theta 1 very close to theta 0, we can write this, we can do an approximation of this likelihood ratio test using a Taylor series expansion, and then we have a locally optimal test. Okay? It's a little bit tricky. You have to be careful. You don't do the approximation and then apply it for arbitrary theta. Okay? There's always a tendency, once you've got a nice clean detector structure, to say, oh, well, I'm just going to use it in general. But it's not valid in general. It's only valid around the parameter around which you made that approximation. Okay? All right, so I think we have about half an hour, so I think I want to go ahead and work on the, I obviously didn't do a review of the first half of the class, but I'm assuming that that's not really necessary. So let me go over the practice exam and give you some idea of the results. I don't know if you have gone over it or not. I hope you did. It's certainly helpful. Okay, so let me zoom in on this. very well focused, is it? There we go. Okay, so the first question, the expected value of x to the 8th, well here I said explanations and derivations will not be graded, but I don't do that anymore. If you put an explanation, that's fine. The expected value of x to the 8th given y is bigger than or equal to the expected value of x squared given y raised to the 4th power. Is this true or false? Anybody try this?
Is there any x and y are uncorrelated?
There's no conditions on x and y. I mean, obviously, if they're uncorrelated, then the conditioning doesn't give you any information, right? But even if that was the case, it's still not obvious that expected value of x to the 8 is bigger than or equal to expected value of x squared. I mean, even if you get rid of y, that still doesn't give you an obvious answer, right? Okay. So the idea here is, what you do is the following. You look at the variance of x to the 4th given y. And like I said, if you get rid of the given y, the argument still works. So this turns out to be the expected value of x to the 8th given y minus the expected value of x to the 4th given y squared. Right? Oh, you can't see it? Wow, this is huge. Yeah. Okay. Maybe I should use a different pen. Okay? So, if you look at this is a variance, right? So this quantity here has to be bigger than or equal to 0. Right? I've just written the definition of the variance of x to the 4th. Okay? Now I'm not quite done yet because this is actually x squared to the 4th, whereas this is x to the 4th squared. But then what I'm going to do is I'm going to write the definition. I can write the definition of the variance of x squared again, and I get another term here that behaves the same way. And then you'll see that this is true. Okay. So actually, let me do it on another piece of paper because I think it's really difficult to read it on this. Okay, so problem 1. So variance of x to the 4th. Let me just get rid of the condition on y. This is the expected value of x to the 8th minus the expected value of x to the 4th squared, which is positive, right? And then the variance of x squared is the expected value of x to the 4th minus expected value of x squared, which is also positive. Okay? And then if you just combine these together, this means that the expected value of x to the 8th is bigger than or equal to the expected value of x squared to the 4th. That's it. Okay? Just a little trick.
Can we start with the Cauchy-Schwarz inequality?
You could. That's another way to go about it, yeah. Okay, but I mean the trick is you just have to write this and then remember that this has to be bigger than or equal to 0 because of the definition of the variance. And that's really I mean, writing this part is not that complicated. Just remembering that this has to be positive, that's kind of the key issue. Okay. All right, the second part is exactly one of the problems that was in the midterm. So I'm not even going to bother going over it. Part C, the question is, minimum variance on biased estimators always achieve a lower mean squared error than maximum likelihood estimators. Okay? So, by the way, so this is, then the answer to this is true, right? So, the next problem says, minimum variance on biased estimators always achieve a lower mean squared error than maximum likelihood estimators. So let me put it up here. Maybe you can see it better.
False.
False because
There's no guarantee to do that.
well, the answer is false. That's correct. The real reasoning that you want to do is that you can say maximum likelihood estimators don't have to be unbiased, right? And so they can have bias, and if they can have bias, then they can have lower mean squared error. So that's the way to argue it. Okay. So part C is false. All right, and then now let's go to part D. If an efficient, this is like a monster finger. If an efficient estimator exists, it must coincide with the minimum variance unbiased estimator. Okay? Oh, this is efficient meaning no bias. Okay? So unbiased. So the answer is
False.
why?
Because the minimum variance unbiased estimator does not need to be an efficient estimator.
Okay, but this is going the other way. Okay? So the answer is true. And the reason it's true is the following. If an efficient estimator exists, so remember this result. If an efficient estimator exists, it is the maximum likelihood estimator. Okay? And then that maximum likelihood estimator will achieve minimum variance. So this could be true. Okay. All right. So let's see. We don't have a whole lot of time. Let me go back and try to solve these problems now. Okay. So the next problem is if you have. Let's see if we can describe this. It's actually a lot easier since we don't have a whole lot of time if I just show you how it works as opposed to try to solve it. Okay, so the idea, jeez, you can't really see this, can you? Okay, so you walk into a bank with two tellers, right? Two people to help you. And you know that one of the tellers' service time, the length of time it takes to help you, is an exponential random variable. So the distribution there is 2 times e to the minus 2x1. And the other teller's service time is a uniform random variable in the range 0 to 3. And you don't know which teller is which, so you just pick one at random, in other words, with probability 1/2. And then you stand in that teller's line. You measure how much time it takes for that teller to help you. Okay, and that becomes your measurement, y. Now, based on that measurement, based on that service time, the observed service time, you want to specify the optimal rule, T of y, for deciding whether you picked teller 1 or teller 2. And the condition that you want to satisfy here is that the rule should minimize the probability of error. So you want the minimum probability of error decision rule. And you want to use your answer in terms of intervals of y. So the first thing to do is to write down the probability density functions for these two scenarios. So if H1 is teller 1 and H2 is teller 2, these are two hypotheses. This is the PDF for H1, this is the PDF for H2. Okay? And it's important to make sure that you write down the range of these probability densities carefully. Okay, so this one is positive, from positive y. This is equal to 1/3 for y between 0 and 3, and it's 0 everywhere else. Okay? And now you just write down the minimum probability of error decision rule with equal prior probabilities. And the decision rule is simply this. With the right-hand side is a ratio of 1/2 to 1/2. So it's just 1. And you simplify, and you get that y is 1/2 log of 6. Okay? The only tricky part in this problem is that you have a negative in the exponential, and so what's going to happen is once you take the log of this and you get rid of the negative sign, these two inequalities have to flip. Okay? So here I have h1 and h2. In the final answer, it's h2 and h1. And if you just miss that and you write h1 and h2, wrong answer. Okay? That's not a minor mistake. All right? I'm just being straight with you. That's a big error. Okay? I had a student in one of my other classes, an undergraduate class that I was teaching, come and argue with me about a grade. Right? And he said, well, you know, why didn't you give me full credit here? I only made a small mistake. And I said, well, let's say you're an engineer and you make a small mistake in building a bridge. I don't want to go on that bridge. Do you? So it's the same thing here. Okay, these are not small mistakes. All right, so then if you want to specify the region then the region is like this. This expression that we just looked at said that y has to be bigger than this 1/2 log of 6, which is about 0.9. However, you have to remember the range of the distributions, right? So here you've got h1, here you've got h2, here you've got h1 again. Okay? Because remember, one of them is a uniform distribution, so it goes only from 0 to 3. Okay? And so you have to specify the range in this fashion. So I don't know if it's clear or not. Let me go back here. So y is bigger than, if it's bigger than this 0.9, you get h2. If it's less, you get h1. So that's reflected here. But then there's these other intervals you have to also make sure you take care of. Okay? And then the second part of the question is find the probability of error. Find this value of the minimum probability of error. So probability of error is 1/2 the probability of choosing h2 given h1 plus 1/2 probability of choosing h1 given h2. And these 1/2s are precisely the 1/2s that you use in choosing which teller you go and stand in line. Then the probabilities are written in this fashion. You just write the range. Now, this is the reason why you have to be careful about this range. Right? You have to specify these regions very carefully because now you're going to use them. Now you're going to do some integrals. And if these ranges are not specified properly, you're going to get these answers wrong. Okay? So then you just integrate. These are the integrals of the two pieces. You simplify, you get this, which is on the order of 0.23. Okay. Questions?
Do we have to give a numerical estimate?
Oh, you mean from here to here?
Yeah.
No. I mean, if you get something this ugly and you just leave it like that, that's fine. Okay. One thing I do expect you to do, though, is the following. You should be able to give yourself the opportunity to check if your answer makes logical sense or not. So for instance, remember this is a probability of error, right? If this here was a negative number, you've got the wrong answer, okay? So although I don't expect you to simplify it, I do expect you to check if your number makes sense, all right? So I don't want to completely absolve you of all responsibility when it comes to checking your answer. I always try to give things that don't require too much calculation so that you don't have to pull out your calculator, but still. Okay. Let's go to the next one. All right, so this one, you have a composite hypothesis testing problem. You make n independent and identically distributed observations, and you have two hypotheses. In one of them, the first one, you have an exponential random variable, that's this first one, And in the second one, you have x e to the minus x, so that's not quite exponential. Alpha and beta are two deterministic unknown parameters. X is positive for both of these situations. And what you're asked to do is to derive the generalized likelihood ratio test detector for this problem and simplify the result as much as possible. So the procedure here is you take all of your data and you compute maximum likelihood estimates of alpha and beta. Then you plug in those maximum likelihood estimates into the expression for the likelihood ratio test, and you simplify the result. Okay? What you don't want to do is write the likelihood ratio test, simplify it, and then plug in estimates of alpha and beta. Is that clear? So write down the likelihood ratio test, plug in estimates of alpha and beta, then simplify. All right, so one of the most common errors that I see in exams is people simply forget that you have n samples. Okay? You write everything correctly, but you just forget that you have n samples. So if you have n samples, the first thing you need to do is to compute the joint probability density function for all the samples. And so if you just write this P of x given H0 and alpha, if you just rewrite what I gave you, that's no good. You have to write the joint density, which is the product of all the individual densities, because these are independent, identically distributed. So you get this. And for the second case, same thing. Again, you multiply a bunch of these independent, identically distributed, multiply the PDFs for these IID samples. Then you compute maximum likely estimates for alpha and beta. How do you do that? You take the first one, you take the log of this density, differentiate with respect to alpha, solve, set it equal to 0, and solve. You get alpha hat equals the average of the data. Okay? Do the same thing for the second density, for the second joint density. And you get another equation which you solve. And beta hat becomes 1 over 2n, the sum of xi. So in fact, the only difference between these two parameters is that one of them is the average, the other one is 1/2 the average. Okay? Then we do the GLRT. Okay, so you write the GLRT up there, you plug in alpha hat and simplify. There's a bunch of algebra that you have to do, you have to be careful about. And what you end up with is the following equation, or following inequality. In the numerator is the product of all the xi's raised to the nth power, or 1 over nth power, and in the denominator is the average of the data. And on the right-hand side, you've got this gamma over 4e. E is just, the e number, like e to the whatever. There's an interesting interpretation of this. The numerator is the geometric mean. Geometric mean of a bunch of numbers is when you multiply them and then you take the nth root. Okay? And the denominator is the arithmetic mean. So what this says is the GLRT is the ratio of the geometric to the arithmetic mean of the data for this particular example. Okay, and then the second part is supposing that the underlying parameters are equal, which parameters do you think is harder to estimate and why? Well, when I say hard, which one is harder to estimate, what I'm really referring to is which one is going to have the highest variance or the highest mean squared error if their underlying values of alpha and beta are equal. So all you do is you're going to calculate the Cramer-Rao bound. That's one very good way of predicting the hardness of the problem. So you compute the Cramer-Rao bound for alpha and beta. For alpha, the Cramer-Rao bound turns out to be alpha squared over n. And for beta, it turns out to be beta squared over 2n. It turns out that both of these are in fact efficient estimators because the maximum likelihood estimates in fact have this variance. So if you remember the ML estimates for alpha and beta, you can in fact find the variance of these things, and what you'll see is that they in fact coincide with these numbers. So you have efficient estimators in both cases, and so if alpha and beta are equal, there's a factor of 2 difference between these two, which means that beta is easier to estimate because it has a smaller variance. Okay? So it's not a very complicated question at all. Okay, so number 4. Okay, we want to determine the unknown probability of heads when flipping a coin. So the idea here is this is an estimation problem, and you're given a coin, and you're asked to find whether this coin is fair or not. Okay, so you're going to flip the coin, and you're going to estimate the probability that you're going to get heads, and you're going to estimate the probability that you're going to get tails. How are you going to do it? You're going to flip it n times in succession, each toss statistically independent of the others, and with an unknown probability of heads or tails. And once you've done this, you're going to observe m, which is the number of heads that you've drawn. Okay, so you toss n times and you observe m heads. Now find the maximum likelihood estimate of alpha, which is the probability of heads, based on the observed m. Now, first of all, just intuitively, what's the probability? It's just the ratio of the two, right? But I'm asking you here a very specific way of calculating that probability, which is maximum likelihood. So what do? You have to actually go through the process. So if you stop at this point and say, hey, I know what the answer is, m over n, stop. 0 credit. Okay? You have to go through the steps. You have to show the steps. So what we do is we define a Bernoulli random variable. I'm not able to see it here. Okay, for the ith toss, you define this random variable xi. Given alpha, this PDF is going to have value alpha or 1 minus alpha, depending on whether you get 1 or 0. And so you get this PDF, alpha to the xi times 1 minus alpha to the 1 minus xi. And with n tosses, then the joint PDF for xi is going to be the product of these independent PDFs. So what you end up with is this joint density. PDF of x given alpha is this joint density. So this is, again, what you've done is you've written down a probability density function with an unknown parameter, which is alpha. All right, now we want to do maximum likelihood estimation of alpha. So you take the log, which is this next line. You take the derivative of the log, you set it equal to 0. You solve, and lo and behold, alpha hat maximum likelihood is in fact m over n. Okay? So this kind of very intuitive estimate that you immediately thought of is in fact the most likely value of alpha given the data that you have. Okay, and now you want to see if it's unbiased. The question is asking you, is this an unbiased estimator? It's actually asking you find the mean squared error of this maximum likelihood estimator. So you're going to do two things. You're going to find the bias, you're going to find the variance, you're going to add the variance to the square of the bias, and you're going to report to me the mean squared error. Okay, so here's the expected value of alpha hat. It's unbiased because it's equal to alpha. Then the next step is you compute the variance. The variance right here. And that turns out to be alpha times 1 minus alpha. For each xi, the variance of alpha hat is 1 over n squared times the sum of the variance of xi's. So the variance turns out to be this expression, 1 over n times alpha, 1 minus alpha. Then the mean squared error is variance plus the square of the bias, which is 0. So this is the variance, 1 over n alpha, 1 minus alpha. Okay, so that's also the mean squared error. And what you can see is that the mean squared error in fact decays to 0 as you have infinitely many tosses. Right? So what is this saying? It says you can exactly figure out the probability of getting heads if you're willing to sit there and toss the coin infinitely many times. Okay? Because the mean squared error goes to 0. And then the final part is the ML estimate efficient? Okay, how do we do that? We find the Cramer-Rao bound, the Kramer-Rao bound turns out to be n over alpha times 1 minus alpha. And now if you look up here, you have an unbiased estimator with mean squared error, which is exactly the same as the Fisher information. Therefore, it is an efficient estimator. It has achieved the Kramer-Rao bound. Okay? End of story. All right, and the last one I'd say is a little bit conceptually tricky. So the idea is you consider the following autoregressive model. So the Zn equals a linear combination of a bunch of other Z's. These are Zn minus 1, Zn minus 2, and so on. Where this linear combination has coefficients theta k which are unknown. And some noise. This is called an autoregressive model because the coefficient, the values of the values of z depend on previous values of z. Okay? How many previous values of z? In this case, p previous values of z. Okay? So for instance, our sequential least squares was basically an autoregressive process because one estimate depended on the previous estimates and so on. Except that here the dependence is only on a small window prior. Okay, so theta k's are unknown and wk are zero mean random noise. They don't have to be Gaussian. And you have data values Zn for 0 to n. And before that, everything is 0. So assuming n is bigger than or equal to p, meaning you have more measurements than you have parameters, estimate the parameters theta, given this data. So here you have to be a little bit disciplined about the way you write things down. And so the way you write things down is z is a vector that goes from 1 to n. Now remember, we had actually n plus 1 data points, right? So the data went from z0 to zn. Okay? But here I'm defining the z here to go from only 1 to n for a very specific reason. If you look at z1, z1 is a linear combination of the z's that came behind it, p of them. So they are going to be in this row, and they're going to be multiplying theta 1 through theta p. And then there's some noise. Z2 is again a linear combination of the last p z's with these coefficients and so on. So I can now write down this equation where z is this vector of data, h is a matrix composed of the previous values of z, theta is the unknown, plus w. Right? Okay. So the question now is to find the least squares estimate of theta. Okay, so also remember that I told you for Zn equals, for n values less than 0, everything is 0. So this is just going to be a p by n matrix where this upper triangular part is going to be 0. Okay, so what's the least squares estimate? The least squares estimate is simply this guy here, right? H transpose H inverse H transpose Z. Now, the question, probably the trickiest part of this problem, is the last part of the question asks, if the noise is Gaussian and white, is the above least squares estimate also the maximum likelihood estimate? Okay. Remember, we talked earlier about how the standard least squares problem gives you a solution that is exactly the same as maximum likelihood when the noise is Gaussian. And I'm asking you, is that true here? Okay? And you look at this and you think back, and the obvious answer seems to be yes. But in fact, the answer is no. And the reason the answer is no is because for ordinary least squares, H is in fact known perfectly. Okay? However, in this case, H itself is a bunch of noisy measurements of Z. So H depends on the data. In standard least squares, H does not depend on the data. So, in this case, in fact, even though everything looks exactly the same, because H depends on Z, this is not the maximum likelihood estimate anymore. It is still least squares, still a perfectly legitimate estimator, but it no longer coincides exactly with the maximum likelihood, even though the noise is Gaussian. Okay? And of course, you know, if you think that maximum likelihood and least squares always coincide, this is clearly a contradiction to that. So you should not always assume that maximum likelihood and least squares coincide, unless some very specific conditions are satisfied. Okay? All right. That's it. We're done. Good luck.